So thank you for taking the time for my session, BigQuery and Cloud Machine Learning. I'm Kaz Sato. I have been working in Google for the last 6 years. And for the last 2 years, I have been working as a developer advocate, which is like an evangelist for developers. So I usually go to the meetups and events for developers and talking about the products and technologies. And now I'm focusing on the data and analytics, the products such as Google BigQuery and machine learning APIs, TensorFlow, and machine learning engine. Yeah, I sometimes still using the Cloud ML, but we have just changed the name to the ML engine, so I would make some mistakes today. So today I'd like to discuss about these things, how to combine the large-scale data warehouse, that is BigQuery, with machine learning provided by the Cloud Machine Learning Engine, or ML engine. So at first, I'd like to introduce what is BigQuery. How many people have used BigQuery? Oh, most of them, it's like 80%. But I see about 20% people has not used BigQuery. So I'd like to introduce the technology at first. It's a fully managed petabyte scale enterprise data warehouse. To solve this kind of problem, big data problem, if you have terabytes of data and you want to scan all the data stored in this disk drive, in seconds, how do you do that? Do you want to build your own Hadoop cluster? Do you want to build your own Spark cluster, taking the tens of minutes or tens of maybe hours to going through all the scanning all the data? In Google, we don't have times to wait hours. Instead, we have to solve all the problems, like troubleshooting, asking queries. In seconds, we have to solve all the big data related problems in seconds. So to do that, we did some experiment inside Google. If you want to scan all the 1 terabyte of data in 1 second, how many disk drives you would need running in parallel to do the scanning? And the result is that you would need 5,000 to 10,000 disk drives running in parallel to scan all the data, and everything is done in 1 second. And we did that by using the hundreds of thousands of machines in Google Cloud. The Google Cloud is the data center as a computer. That means it's not just a building to host the bunch of the servers. Instead, it is designed to work as a massively parallel computer, single computer. So that means we have been developing all the hardwares and the middleware stacks to deploy your own the jobs or processes or applications on the hundreds of the servers instantly by using a single line of commands. And the most important part of the Google Cloud technology is the network. This is a switch called Jupyter. This is not a commercial commodity switch we have bought from the other manufacturers. We have been spending so much investment on building our own network switch hardware from scratch. Why we are doing that? Because we are trying to consolidate all the server resources like CPUs, memories, and disk server storages, consolidated with the microsecond latency network, so that we can apply the petabit networks and infrastructures to solve many kinds of problems, such as the big data solutions or deep learning technologies. So one of the applications of this petabit network is the BigQuery. That is a massively parallel query, processing query. So that means every single query you would run on BigQuery will be processed by 1,000 to 2,000 CPU cores, hundreds of disk drives in parallel. So that's the reason why you are seeing the outstanding performance when you are using BigQuery. So let's take a look at the very simple demonstration of BigQuery by using the Cloud Data Lab. This is a tool called Cloud Data Lab, which is a Google Cloud version of the Jupyter Notebooks. These days, many data scientists and data analysts are using the Jupyter Notebooks, which is a web browser-based analytics platform. And we have combined the Google Cloud platform with Jupyter Notebooks. So it's just like the Jupyter Notebooks. You can run any arbitrary Python code inside the browser. And also, you can access to the Google Cloud services, such as the BigQuery, Google Cloud Storage, TensorFlow, Cloud Machine Learning, or ML engine, inside the data lab Python code. So you can write the SQL for BigQuery inside the data lab, just like you are seeing right now. And this is a sample query I am running to scan all the data on a Wiki 10b table, which has the 10 billion rows of the Wikipedia update logs. So let me run that. So what it is doing now? So it is a simple query to scanning all the 10 billion rows to find out all the rows with the word Google inside title by using the regular expression match. And usually, if you write this kind of query that requires full scanning or table scan of your table, that means you have to read all the data stored in the disk drives, read to the CPU, and using CPU do the pattern matching on it. Usually, your database administrator would be so mad at you because, most important part of the database design is to build the index to get the reasonable performance. But by using the things like regular expression matching or text pattern matchings, there's no way to build the index. So that means you have to download all the data from the disk drives, process everything on the CPU. But still, you can get the result. You just saw you were able to get the result in 5 seconds. I think I'm not getting a correct result. Let me try it. Okay, like a wiki. Let me try with the other. Okay, so by clicking on the user interface of the data lab, you can easily execute the query again and again, and you get the result. This is not a cached result. It actually scanned all the data stored in disk drives, the hundreds of disk drives in parallel, scanned 400 gigabytes in real time, and got the result within 5 seconds. So this is the performance you could get at a very inexpensive cost, reasonable, the cloud, the economy of the cloud. Why we can do that? Because we are using the 1,000 or 2,000 CPU cores and hundreds of disk drives in parallel just for single query. And it's affordable. This is the power of the BigQuery. So it's fully managed and requires no special database administrator. And it can process the terabytes of data in tens of seconds. It's so fast. Actually, I can say that, I joined Google 6 years ago, and I instantly noticed that this technology is called Dremel in Google, and we have been using Dremel since 2006. And this is one of the core technologies we have been using inside Google. And that is the one reason why Google has been so successful. Because every teams, like Android teams, YouTube teams, Chrome teams, Gmail teams, can access the terabytes of data in tens of seconds by using this tool. So that's the largest difference I've seen when I joined Google 6 years ago. And it also provides the economy of cloud, so you don't have to buy the expensive the data warehouse appliance, which costs like $1 million, $2 million. But I sometimes get the feedback from the BigQuery customers. I always talk about the performance of BigQuery, but they say the performance is not the highest priority. For the BigQuery users, the most important part is the ease of access. Why is that? Because the BigQuery is scalable, because it shares the thousands or tens of thousands of CPU cores and disk storage on Google Cloud. That means it's so scalable. So even if single user can run a very slow performance SQL, or the SQL that requires so much server resource, it doesn't affect to the overall service, or other users will not be affected by the slow users or slow SQL. So that means you can allow any users in your enterprise accessing to the BigQuery directly with their homebrew SQL or quick and dirty SQL that is stored on your notepad or spreadsheet. Usually, if you do these things with your the existing data warehouse systems or any database systems, the database admin would upset about that, so they don't allow it. But now BigQuery user is allowing the people, the business people, sales people, market researchers, and support personnel to directly execute the SQL from their spreadsheet or web UI to BigQuery to get real-time data. And still, nobody would be affected for performance. So we call it as the democratization of data. So now BigQuery can allow everybody can access to the enterprise data in real time. So that's the basic of the BigQuery. But still, it's just an ordinary SQL data warehouse. So you can write the standard SQL, like the select statement with where clause and group by, order by. Those are the same old SQL. But how you can make it smart, how you can implement the smarter analytics by using the BigQuery. Here I call it the concept called signatures. By signatures, I mean the feature vectors taken from the content, so that you can make the BigQuery SQL a little bit smarter. And I can show the demonstration of the smarter query by using a demonstration called Query Smart. This is a demonstration we have built for the next Google Cloud Next today. And you can see the same demonstrations on the sandbox area, the playground area. So anyone who's interested, you can go to the demo area and try it by yourself. If you start the demonstration, we have the 3 different demonstrations inside this demo, and we are choosing the document search. And this is where you can select the key document. This is all about the document similarity search. We have stored over 10 million of the Stack Overflow questions stored on BigQuery as a public data set. And you can do the similarity search on document based on its content. So let me check this one as a key document. So now the BigQuery is executing the query on the 10 million documents from the Stack Overflow to find the similar documents. And this is not about a keyword match or pattern matching. This is comparing all the documents, each other, to find the similarity between the documents. And I got the query finished. So this is the key document at the left. And in the middle, you can have the list of the similar documents. So by clicking each one of them, you can see the BigQuery was able to find the similar documents. Based on the scores you can get, that represents the similarity between the documents. So how do you implement this kind of a little bit smarter query with BigQuery? How do you find a similar post on the Stack Overflow? So to implement this, we have implemented these things. At first, you can split all the statements split into the words, and then you can extract the signatures. By signatures, I mean the feature vectors for each post. That represents the content inside each post. And you can define the user-defined function. User-defined function is a feature in a BigQuery where you can write any JavaScript code to define a function that could be used in the SQL query. So by using a user-defined function, you can calculate the similarity between the signatures of 2 different documents. And use the user-defined function in your arbitrary SQL to find similar documents. And there is a big difference between the feature vector-based search and the keyword match search. Traditionally, in any data warehouse systems, people have been using the keyword match, like specifying the tags for the content, like a movie or music actor, and checks if each document or content has certain tags or not. But instead, where I'd like to propose is to use a feature vector for comparing or searching for content. By feature vectors, you mean that there's a vector and dimensional vector that represents the content of the documents. So how do you extract the feature vectors? So by taking a look at this screen, you can see that the feature vectors actually holds the pairs of the keywords and scores of keywords. For example, this particular document uses the word add and class and element. This document uses the words such as the differences between or hash map. So those are the all important words. There are some algorithms used for this extracting for featured vectors that can get rid of all the trivial words such as the in or to or are or that or there. So by using the algorithms called TF-IDF, you can extract the most important word used in the content and put the scores on each word. So that is the feature vector or signature we can use to do the similarity search between contents. So if you put these feature vectors in a or in a n-dimensional space, you look like this. So if you try to find the similar documents in an n-dimensional space, you have to take the cosine similarity. That means if you have two vectors, you are looking at the angles between the two vectors. So if you find another vector which has a very narrow angle, that means you are finding the similar documents or content. And then you can define a user-defined function to get the similarity, calculation the similarity between the two different documents. And it's just a basic math. It's just a multiplication and additions you learned in the high school, so it's not so hard. It's not a machine learning yet. Let me actually do what I have explained inside the data lab. So again, the data lab, I have written all the SQL and scripts required to do this. So at first, take a look at what will be the Stack Overflow post you can access from the BigQuery. So on BigQuery, we have a bunch of the public data sets, such as the New York City taxi, the logs or the accidents. And one of them is the Stack Overflow post. As you can see, you can access to the any posts like titles or body of the question, or accessible from any BigQuery user. And what you have to do at first is do the segmentation. And here I have defined a very simple function called segmentation that has the regular expression to remove all the HTML tags and extracting the English words from the content. So by executing this query, you'll be getting the array of words. So you see the result. By using the simple user UDF, you can extract the words, split this sentence into the words, like how to check in one string context. So this is the first step. Then what you do is to calculate the feature vectors by using TF-IDF. As I mentioned, by using the TF-IDF, you can get rid of all the trivial words and leave all the important words for each document. Let me execute it. It has about 20 lines of the JavaScript code, so it's so easy, not so hard. It's much easier than defining your own neural network. So I got the result. So as you can see, each TF-IDF feature vector contains a very important words and its scores. That represents the content of the document. So now we can use these feature vectors for similarity search. Again, we are defining another UDF called calculate similarity between the two documents. This is much easier to define. So all you have to do is to write like 10 lines of JavaScript code to get the cosine similarity here, and use the calculation, use the functions just like this, and use that similarity to sort out based on the scores. So let me execute the query now. So running it. And you'll be getting the result in maybe 15 or 16 seconds. Still running. Oh, you got it. So these are all the similar posts against the target document. So as you can see, it is talking, all of the document is talking something about the MLSQL server and how to add or delete column. So you can see that this is not just a simple keyword search or pattern matching. This compares the content of each document to each other and get the similarity between them. And now I have explained how you can use the BigQuery user-defined function to do the vector operations so that you can handle things like the feature vectors as signatures of each content. And you can actually apply these technologies to any kind of content, like document, not only the document, you can apply it to the unstructured data, like images or audio or any business data, like your product or users, or anything. And now we are trying to combine the machine learning engine, the power of machine learning, to extract the feature vector or signature from your content. So if you have the bunch of the unstructured data like images or content or natural language, how to extract the things like human sense or instinct? For example, if you have an e-commerce site where you are selling the many fashion items, but the taste for the fashion items by the buyers would be defined by the senses or instincts. You cannot write any Python code or Java code to define the conditions like if statements to define if you have this kind of the data, then this shirt would be liked by this woman or this man. Yeah, it is really hard. It must be hard. So that's the limitation of the existing IT system. Instead, we can use the machine learning or neural networks to extract the features from the data set so that the neural networks can extract the features to let the computer learn what is the conditions or what is that instinct or senses they are using for selecting the fashion items in the e-commerce site. Let me actually show the live demonstration of the neural network. This is a demonstration called Playground, where you can actually define your neural networks inside the browser and learn the training against the training data set. And here I have a training data set called double spiral, where you have two spirals. One is the orange spiral, and another is the blue spiral. And we have the x1 and x2, two data as an input. And if you're a human, for human, it's really easy to understand the patterns. If you have new data here, it should be in the orange spiral. If you have new data here, it should be in a blue spiral. For humans, it's so easy by telling by your instinct. But how do you let the computer understand the underlying the patterns in the data set? How do you write the programs to classify this problem? Do you want to write many if statements with many conditions, whether each dot is in this area or whether each dot is in this area? This doesn't work. Maybe you can do that, but I don't want to do that. So instead, I would want to use the machine learning or neural networks to solve this problem. So let me start training this model. So now we have started the training of the neural networks. Every neural network in the world doesn't make any sense on the data at first before starting training. But if you keep training the neural network model with your training data, then gradually computer tries to extract certain patterns hidden inside your data set, just like you see. So now the neural network model is smart enough to understand there's a double spiral pattern inside data set. So that's how the machine learning can get smart, and sometimes get smarter than humans, because it can extract the hidden features from a data set. And if you take a look at what each neurons are doing inside neural networks, actually each neurons, artificial neurons in the neural networks is doing very similar thing. The real neurons in human brains does also very simple things. We have about 100 billion neurons in single brain, and each neuron is just get excited or not by receiving the electricity from the other neurons signals. So if you are watching the very bright light or listening to the very the loud noises, our neurons inside the brain will be get excited or not. And we have so many connections between neurons that represents the knowledge and intelligence of humans. And with the artificial neural networks, we are trying to mimic the behavior. With the current technology, it is impossible to simulate the whole behavior inside human brain. It is not possible yet, but still we can mimic the behavior. So that the whole idea of neural network is to mimic the how the people are using the signals from outside and using the networks between the neurons to do the intelligent information processing. So just like the neurons in humans, each neurons in the artificial neural networks does very simple things. For example, if you take a look at this particular neuron, it only classifies the data points is in the blue area or white area by drawing a straight line here, just like it. It's very simple. This neurons draw a straight line again and checks whether your data point is in blue area or white area. Get excited or not excited. So that's so simple. But if you have a bunch of neurons and multiple layers, the hierarchy of neurons, then something interesting is happening here. So the neurons in the second hidden layers can take all the outputs from the first layer and make a little bit smarter decisions by combining all the results from the first layer. So you can see the patterns used in the second layer is a little bit smarter than the first layer. And neurons in the third layer get much smarter. So by combining all the outputs from the 8 neurons in the second layer, it can capture the very complex pattern inside the data set, like you see. And we have the final neurons on the output layer. This is smart enough to understand the double spiral pattern. So this is how the AlphaGo, the Go-playing AI tool, was able to beat the world-class champion for Go. This is how the people are excited with the AI right now, because deep neural networks can sometimes exceed the performance of the humans by taking a look at the patterns, extracting patterns from the data set. So this is all about AI, and we provide a bunch of the services from Google Cloud that let you take advantage of the power of the machine learning. We provide 2 different kinds of products. One is the pre-trained ML model. Another provides the custom ML model. So if you have your own data already, like images or the audio or natural language text, then you can put everything on the pre-trained ML model API so that you can get the result faster. So if you send your image of a cat to the Vision API, you'll be receiving the labels such as cat instantly. Or if you want to solve your own problem with your own training data, then we recommend you to build your own neural network definition with TensorFlow and train it by using the ML engine. That provides the full managed distributed training model for you. So Cloud ML Engine is a fully managed TensorFlow platform for Google Cloud. It provides the distributed training and prediction model, and it scales to tens of CPUs and GPUs. And the most challenging part of using deep learning technology right now is the computing power you have to consume. So even if you have the very powerful GPU server, single server, it takes a few days or sometimes a few weeks to finish all the trainings, to train your own model. So that's the hardest part. That is the reason why not everybody has started using deep learning. It's too hard to build your own GPU cluster by yourself. Instead, now we have a bunch of GPUs on Google Cloud. So you can just rent 10 or maybe 100 of GPU from Google Cloud just for 1 hour. It takes so less cost. It's not expensive. So by using the Google Cloud machine learning engine, you don't have to spend much money to getting started with the deep learning technology. So we have learned what is machine learning engine and what the neural networks does. And let's think about how we can combine these technologies with BigQuery. The one use case is to use BigQuery for preprocessing the training data. So the TensorFlow or the machine learning engine or ML engine itself is not suited for all the preprocessing or collecting all the data from enterprise systems. So you can use BigQuery as a data lake, so you can gather all the data coming from the enterprise, like application server, web server, databases, all imported to the BigQuery and do some preprocessing on that. Then you can export the data as a training data to the TensorFlow or ML engine. So let's take a look at the actual demonstration for that. Here, I'd like to use the Cloud Data Lab to use the BigQuery for preparation or preprocessing, and use the TensorFlow to train the neural network model for machine learning analytics. So this is the sample code I have prepared that is called Classifying Manhattan. Here we are importing the bunch of the location data from BigQuery and train the neural network model to classify whether each location is Manhattan or not. So let me clear all the cells first. Now let's take a look at what kind of the training dataset we'll be using by executing this query. So I'll be using another public dataset called NYPD collisions that records all the car accidents happened in the New York City with its timestamp and borrow latitude and longitude. But you cannot use this raw data as it is. You have to do preprocessing to that because you can see that some rows doesn't have any borrow data, some rows doesn't have any latitude and longitude, and we have to remove those useless garbage data. So again, you can use the BigQuery to do this kind of the preprocessing. And also, I want to have a new program, is Manhattan, to have a flag. That flag represents whether the latitude and longitude is inside Manhattan or not. So this is the SQL I'll be using for preprocessing, and let me execute it. And also, you can also execute another code to extract all the data from BigQuery, import it into the Python. So now you have all the data imported into Python code. So as you can see, by using Cloud Data Lab, you can seamlessly integrate the BigQuery query with the Python code you write. And you can continue to use your scikit-learn or the NumPy code running on BigQuery. Sorry about my voice. So now we have the training dataset. One is Manhattan. This could be used as a label for training, whether each location is in Manhattan or not, and pairs of the latitude and longitude for 10,000 rows. So let's do the feature scaling. Before starting training, usually in machine learning, you have to clean the data out, or cleansing of the data. And one important thing is to do is the feature scaling. And if you do the scaling and plotting the data, you can see the training data set would look like this. Now, everything is centered on the 0, but still you can see the shape of the Manhattan here. And you can even see there's a Central Park inside the data set. So this will be the training data set for neural network. We'll be splitting the data into training data and test data, and use TensorFlow to define your neural network. Here I'm using TensorFlow, especially the so-called high-level API of TensorFlow. And this is one of the features we have recently announced with TensorFlow 1.0, where you can just run a few lines of Python code to define neural networks. Before that, we have been using so-called low-level API, where you have to define all the computation graph, low-level computation graph to define your own neural networks. But now you can just write a few lines of code with Python. So you can see we are defining deep neural networks with the 4 hidden layers, and each hidden layer has 20 nodes. So we have defined neural networks. Let's check the current accuracy of the neural networks and how these neural networks can classify the Manhattan before doing the actual training. So now you'll be seeing the map classify the neural networks. So this is how neural network thinks where the Manhattan is before training. So because this is before training, the neural networks is stupid enough. It's too stupid to classify Manhattan. He thinks this is the Manhattan. So this is where we have to train the neural network model. The accuracy is 75%. So you can write a for loop to repeatedly call the fit method to train the model by using the training data set. So now it should be gradually showing the better accuracy. So you are seeing that neural network model is trying to adjust how to classify each data points to get better result. So that network is getting much smarter and smarter, as you have saw on the playground demonstration. Yes, it's getting much, much better. So now training is finished. We got the 99.8% accuracy. And now neural network is trained to split the Manhattan and Brooklyn with the very sophisticated curve between them. So this is how you can combine BigQuery for preprocessing and TensorFlow to do the better analytics on it. So that was use case number 1, using the BigQuery for preprocessing. And use case number 2 is to use the BigQuery for signature-based search based on the result you got from the data model you trained with the machine learning engine. We use the ML engine for extracting the feature vectors. So I'd like to show another demonstration of BigQuery Smart. So if you go to Query Smart, you have another demonstration called image search. And you can choose one of the key images. Let me try with the elephant. So we'll be using this elephant image as a key image and compared 1 million images with this key image to find the similar images on BigQuery. And we got it. And BigQuery has processed 8.8 gigabit data over the 1 million images in 10 seconds. And all you see is the similar images. And you may notice that you also have the images that is not elephant, like this. This is not an elephant. But still, it looks similar to the neural networks. And this is apparently is not an animal, it's a statue, but still the neural network thinks it must be similar thing. This is not an elephant, but it has the same kind of the texture or patterns. So the neural network thinks they are similar. So this is not a keyword search or pattern matching, but they are comparing all the feature vectors or signatures of the images. So you can get the much smarter search on the BigQuery. So how do you do this? At first, we have imported all the 1 million images from Wikimedia on the Google Cloud storage. And then we have used machine learning engine, ML engine, to learn the convolutional neural networks on the ML engine. This is a typical neural network design used for the analyzing the images. But usually, people are using CNN to get the labels for the images, such as, is it a cat, is it a human face, is it a flower? But instead of getting labels, we are using CNN to extract the feature vectors that could be in signatures of all images. And by using the BigQuery and UDF, you can do the similarity search against images. And we have used VGG16, which is a popular CNN design, and we are extracting the feature vectors from the final fully connectional layers. And you can do this by writing a very simple TensorFlow code like this. So you can specify which layer you want to extract the vector from. And then you can run the gcloud command to execute cloud ML job to extract the features from the images. Usually it takes hours to run these jobs against the millions of images. So that now we have the signatures of images, feature vectors. And you can find the similarity of distance between the vectors to find the similar images. Again, we are using the UDF to calculate the similarity between the two vectors. It's a very simple math. And you can use the UDF in your own SQL. Just like the ordering by the distance between the vectors. And it's so inexpensive. If you run this query against 1 million images, it would only cost 86 cents. So it's not so expensive. So that was the things I wanted to share to how you can combine the ML engine, machine learning, with BigQuery by using the feature vectors. And at last, I'd like to share another interesting use case of the BigQuery, which is a large-scale demand forecast. Again, I'd like to go back to the BigQuery Smart to show another cool demo. This third demonstration is for speculating or forecasting the demand for New York City bikes. So as a public data set, we have all the record for the usage for New York City bike for past few years. And by training the neural network model, by using the past history, you can do the demand forecast against for specified conditions, like the month in a year, or a day in a week, or weather, or the temperature of the day. And you can forecast how much usage you would get with specified conditions by using BigQuery. Usually people will be using things like Apache Hadoop or Spark or maybe TensorFlow to this kind of the complex analytics against your big data. But now you can use BigQuery, just BigQuery, to implement this. So what you are seeing is the animated heat maps that shows the increases or decreases of the demands for each hour. And we have over 600 stations, bike stations in the Manhattan. And by using BigQuery, you can do the massively parallel demand forecast for hundreds of the points within tens of seconds. Usually you have to wait like tens of minutes before finishing your Apache Hadoop job to do this kind of the sophisticated analytics, but you can use the BigQuery to do this thing and get the result in the tens of seconds. So how do you do this? We have defined our neural networks for demand forecast and trained the model by using the ML engine. And then you can import all the neural network model to the cloud storage so that BigQuery user-defined function, or UDF, can read the model from the cloud storage into UDF to do the prediction inside UDF. So you can define UDF like this. As you can see, you can define very simple neural networks by using JavaScript in UDF. If you have read any textbook for neural network, you may remember that people will be using Python or Java code to write this kind of the multi-layer perceptron code. But in this case, we have used JavaScript running on BigQuery to implement the prediction for neural network. And also, you can import all the weights and biases parameters loaded into BigQuery by using Google Cloud Storage. And with UDF, you can upload up to 5 megabytes of any kind of data into UDF. So you have to compress everything into 5 megabytes. So that's the trick. So I want to note that these techniques I have shown, which is the combinations between the BigQuery UDF and machine learning engines, can be applied to any kind of the applications. Anything you can calculate the feature vectors or signatures out of it. And the most important part here is that you can let all the non-engineers or non-data scientists using these machine learning technologies. So once you have data scientists or ML engineers define the UDF and train the model with ML engine, you can let all the enterprises users using the UDF to do the analytics, ad hoc analytics for daily tasks. So you can, sorry about my voice. So you can apply these technologies for demand forecast or recommendation for the products, or who will be the users who behave like these particular users to find out like the premium users or cheating users or spam users, or what would be the similar musics like this for the recommendation. Or you can even apply the technologies for the IoT applications. So if you have any target signal data, you can do the similar search on the signals from the IoT devices to find any defective devices on the IoT platform, or that kind of the use cases. So let me summarize. So you can use the BigQuery provides the fully managed petabyte scale data warehouse. It provides the economy of cloud. It's easy to use. And also, the UDF, user-defined function, is so useful and powerful computing tool that could be utilized to analyze the signatures or feature vectors of any kind of content, rather than using just a simple keyword pattern matching. And you can combine the UDF with machine learning engine or ML engine to extract the signatures by using the training data set created by humans, so that you can extract the sense or instinct of the humans to make this smart, to realize this smarter analytics. And these techniques, UDF plus ML, is available for any kind of the users in the enterprise. You can allow all the enterprise users taking advantage of the power of the machine learning for everyday tasks. So if you are interested in these technologies, you can go to the GitHub and search with Query Smart. And we already have published all the source code I have used on GitHub, so please take a look at. And I'd like to give special thanks to Tomoyuki Chikanaga, who built all the sample codes I have shared today. And there are some other sessions related to the machine learning and BigQuery and big data processing. So if you are interested, please take a look at those sessions too. So thank you so much.